Hi class, this chapter is 5.6 and this is nuclear fission and fusion. It's our last section in chapter 5. So nuclear fission is what we're going to cover first, and it was discovered in 1930s. So an example here is a uranium-235 is hit or comes together with a neutron. This neutron, coming together with this uranium-235, produces a very unstable isotope uranium-236. This uranium isotope does not stay intact very long. It produces two smaller nuclei in the form of krypton-91 and barium-142 plus 3 neutrons. This is a fission reaction. So I found a gift explaining exactly what I stated, and I'm just going to go over it again. So a large nucleus as uranium-235 comes into contact with a neutron, producing an unstable isotope uranium-236. Uranium-236 splits into two smaller and provides 3 neutrons. Each of these neutrons will now come into contact with another uranium-235, and this will keep going. This is a chain reaction, and this produces a huge amount of energy. This is atomic energy. This is atomic bomb. So this is how this occurs, and this is with an extremely small amount of mass that can create this huge amount of energy. So this is again another picture of exactly showing what I just stated. You see the neutron, the different uraniums, what it produces, and 3 neutrons plus energy. This is the chain reaction. This GIF kind of shows that the neutrons hit other uranium 235, and then the same thing happens again. Those will produce, it'll produce 236. 236 will create smaller nuclei that will then again also produce 3 neutrons. Those 3 neutrons will then hit other 235s, and this will keep going, and this is an atomic bomb. So that's pretty much, let's take a step back. One thing I want to say here is that the mass of the products is slightly less than the mass of the starting materials, and that missing mass is the energy that's been converted to the enormous amount of energy that's been produced. And this chain reaction, so these neutrons all have to be close, all the uranium-235s all have to be in close contact to each other to create this environment of a chain reaction. And because if they're not, then this doesn't keep going. But if they are contained where this will be forced to happen, that's where you get this huge amount of energy and you can create an atomic explosion. So now we're going to look at nuclear fission. Nuclear fission is when 2 small nuclei come together to form a larger nucleus. When this happens, mass is lost and a vast amount of energy, more energy than nuclear fission, is released, and this is a fusion reaction. So fusion reactions, nuclear fusion reactions, actually create even larger amounts of energy than a nuclear fission. So where would this type of reaction occur? Well, this occurs in the sun and the stars and provides us with the light and heat we need. It cannot just happen. It has to happen at extremely high temperatures. You get an idea of what the temperature is right there with that lovely big number. So this is where we get our heat and our energy from. And let's look at an example here. So an example of this reaction is hydrogen isotopes combine to form a helium and a neutron and produce energy. So this energy, it may look like energy, but it's huge amounts of energy. That's how we are able to live. So you see the hydrogen isotopes come together to form helium. You have 1 neutron and then the energy. So they're pretty straightforward. There's not really a lot to cover about these, and they might seem easier, hopefully, because you've already gone through the rest of the sections on this. Nuclear fission, nuclear fusion may not seem as difficult as the radiation parts that we've covered. So indicate whether each of the following describes nuclear fission or fusion or both. I'm just going to go through these and we're going to discuss them, or I'm just going to go through them. So a nucleus splits. This is nuclear fission because uranium will then come to be uranium-236, which splits into 2 smaller nuclei. So that's fission. Large amounts of energy are released. That's both. Fission does not give off as much energy as fusion, and if you've seen what an atomic bomb can do, it's hard to believe that there's something that's even stronger than that. Small nuclei form larger nuclei. That's fusion. An example was the hydrogen isotopes that come together that create helium. Hydrogen nuclei, I just said hydrogen, so that's fusion. And several neutrons are released. That's fission, because remember, when uranium-236 it splits apart, it produces 2 small nuclei and 3 neutrons, and those 3 neutrons will then each bombard another uranium-235, which allows this chain reaction to keep occurring. Okay, so we have one equation to do in this chapter. This is supply the missing atomic symbol to complete the equation for the following nuclear fission reaction. Now, I haven't given any examples because we're going to handle this exactly the way that we've been handling the others. It has to match on both sides. The masses have to match, and the atomic number, the protons, has to match. So we handle it the exact same way. So I put it together here. We have 1 neutron, mass is 235, so this equals on this side of the arrow 236. So if we look on this side, now this is the missing number here. So if we wanted to really look at it, it would be more like this, but I put it on here. So let's skip this part right here, but 137 plus a neutron, but wait, there's a 2 in front, and because there's a 2 in front, that means there are 2 neutrons that have to be accounted for. So 137 plus 2 times 1 equals 139. Now let's look at the protons. We have 0 and we have 92. So we have 92 protons on one side of the arrow. Now if we look at the other side, remember we're skipping this here, and we have 52 plus 0, which is 52. So now we have the mass and excuse me, the atomic number of our new isotope. So if we look it up, we can see it's right here. There's 97 and 40, and we can add that in after we look at the periodic table. And that is it. It's very straightforward. It's just like the other ones, even though it's nuclear fission. And here is a chart covering looking at everything that we've looked at in this chapter.